So hello everyone, continue our talk about some notes that I have for the AI engineering book for Chip Huyen. Let's go to the chapter 2 that is entitled Understanding Foundation Models. So like a brief summary of this chapter is an overview of the decision involved in the creation of an application using foundation models, including training data, model architecture, size, and the trade-offs involved in these whole steps. So some questions and some things that topics that we tackle in this chapter are how to evaluate the quality of the training data and its impact on the model performance, addressing the strengths and limitations of the transformer architecture and how to choose the right model size for your application. Techniques for mitigating inconsistency and hallucination in AI models, and the importance of post training and how these techniques could help to, to, to give more meaningful outputs in your AI application. So the first thing that the author mentioned is this this consequence of the foundation models being more trained on English because most of the data that it was trained on was in English. So as a consequence, the LLM will struggle to be better in another language, for example, for Portuguese, for Brazilian Portuguese, for example. But as long as we know that this evolves, the models in each version gets better every day. So this might not be like a super problematic, but it was still relevant to have specialized agents, specialized models trained on different language that are not English. So that's a very important. And also another thing that they mentioned is that uh, the LLMs are good for like more common sense domains, but if we go to more specific like drug discovery or cancer screening, they will like not perform very well as well. Like we have like the benchmarks that could prove this. Uh, so so then we go to the modeling part. So which architecture to choose, which size, how many layers. So in these parts we go uh, much in detail about the transformer architecture and how all the pipelines involved on that. So basically, I didn't go much deeper on this because I've already knew many of the stuffs because I use in my master degree. But um, to summarize all the things, like we have the advantage compared to the previous version is that in a transformer we could have parallelism. We could take a look on the inputs in parallel. We could have um, attention mechanisms that could focus in each part of the whole input, and we don't encode all the feature in only the last hidden layer that we have, for example, for the models like recurrent neural networks like LSTM, long short-term memory. That's a very important thing for the transformer that boost uh, the um, the overall impact of this architecture. So a very nice analogy that Sheep has in the book is that when she talking about the attention mechanism, she makes some analogy about some key components. So for example, the query vector, you can think like as a person looking for information to create a summary, a key vector, uh, like if like a previous token is a page in a book, then each key vector can be seen as a page number in this book, and a value vector that could be like a page content of each page. So that's a very nice analogy. So uh, she go pretty much in deep with some very nice diagrams and flow charts regarding how these mechanism work. But will not go much deeper here because this is like a very common knowledge in many other blog posts and YouTube channels and articles. So this is like a basic understanding. So if anyone wants to go deep, please feel free. But I will not go as deep as the author goes in the book. because I don't think that's the goal also of the book. So talking about the model size part, it's like uh, we know that like models with more parameters often leads to more better performance. So for example, we also can map these as a resource need. For example, if a model with a 7 billion params, each params uh, uh, could be stored in like 2 bytes, we will have like we need like for example 14 billion bytes, which would be like 14 gigabytes by CPU to perform the computation. And then she mentioned about one technique called mixture of experts that tries to divide these parameters into groups, and only a subset of these groups are active. So this leads to less computation and storage need for the application, and is a very common practice using as of today. So the number of parameter could be like a proxy for the model learning capacity. The number of tokens could be a proxy for how much the model learned, and the number of flops could be a proxy for the training cost of this model. She also mentioned about the chinchilla scaling law that allow to understand what is giving a compute optimal training. You need the number of the tokens to be approximately 20 times of the training of the model size. So you compute the model size and you multiply by 20, and you need like the ideal compute optimal for the training for your application. um, Going to the scaling bottleneck, so she mentioned a very valid and important concern regarding like the foundation models use many data, much data, sorry, and it's very really it's concern to see that for the next couple of years we'll have like a plateau that will not like have much more data to train these models, so that would be like very concerning. And also that's raised an important concern regarding some companies like making their data more protected against these bots that are used to train these models. So, for example, talks about Reddit and Stack Overflow that don't allow all the data to be trained on. So that's a very important concern about proprietary data. So with the scaling of these models, we will have um, this lack of data to be trained in the future. Going next to the post training, this is a very very important section of this chapter. So the main thing that post training aims to tackle is like self supervision, optimize the model for the text completion, but not for conversation itself. So without post training, the outputs might have like racist, sexist, rude outputs, and the post training aims to tackle that, like make to these align to more user outputs. So post training have like basically two major steps. The supervised fine tuning, which is like fine tune the model with instruction data to more optimize for conversation. And the next one is the preference fine tune, a very very important part, which is the fine tune the outputs to align to human preference. So that's why we see like some outputs on chat gpt that like basically say that your aligns with you, so says that you are correct. So basically that's the why we have this behavior. And an important mechanism here is like reinforcement learning with human feedback that was introduced in GPT 3.5 and Llama 2. And but we have some other variations of these, for example the direct preference optimization in Llama 3, and also reinforcement learning from AI feedback using on Claude by Anthropic. So basically pre-training evaluates like token level quality, and post-training evaluates user level quality, which is more meaningful for real world applications. Uh, so going deep on the supervised fine tuning, so the idea is to show how the model should behave in the real world examples with instruction data, and the the author also argues that it is important to have highly qualified people for this part, which is very um, controversial because in other parts she mentioned that we we should use more AI stuff for to cover some bottlenecks using human, but we know that the human part in this whole architecture of the AI makes the total value of this, because we feel if you don't have a human part in this whole pipeline, we don't get real value for real world AI applications. So that's a very important thing to that I noticed. And then in the preference fine tune, so um, the as I mentioned, the idea, the main model here is to use reinforcement learning with human feedback. Um, and the idea is to train reward models that scores the foundation model outputs and optimize the foundation model to generate response for each the reward model will give maximum score for more human preference outputs. Um, so going to another important part of the whole architecture of foundation models, we talk about the sampling. So basically, the model will generate its outputs using sampling strategies. It will not. It will showcase. We generate many outputs, but we will like have a probability for this, and the way that we filter these outputs are defined in this sampling mechanism. So we have many fields in the LLMs that control this. One of these is temperature. So for example, for high temperature, we have more predictable outputs, and with uh, more creative outputs, and with lower temperature, we have more predictable outputs. So for higher we have more creativity, and for lower we have more predictability of the outputs of the model. So this will vary based on each AI application, but we also have other other sampling fields, for example, top K setting, that will limit the next probable tokens from candidates using a fixed number. For example, top K would only list the 10 more probable tokens to generate next. And we also have the top P setting that will generate the top more probable candidate, but based on cumulative probability. And yeah, basically that's it for sampling. And last but not least, like we have an important discussion about the structure output. So for example, for some types of applications, we will need to have very structured output for the LLMs. It cannot like be super non-deterministic. So for example, for if you want to pass the generated thing to, for example, for a code for SQL, we need to generate the outputs that aligns with the syntax of the SQL. So if you want to prepare, for example, for an application for an email, we need to make sure that the JSON is correct, expected for the application. And there are many ways to do so. So the first and more common is to use in the prompt. So align in the prompt, instruct the model to follow an expected structure, but there's no guarantee that it will be followed. So we know that LLMs are no determinism, and if the context is too high, it start hallucination and don't follow the schema proposal. So another thing that we could do is to uh, add this as a post processing. So generate the output for the LLM and then use a post processing to align with the code, determinism in code to align with this schema. And another thing is to use constrained sampling, so using the guiding generating during the LLM prediction to set this constraint, and this can be done during the model creation, or we can do this in fine tune. So in the fine tune, we could um, get the foundation model and update some weights in the creation, like to adding more examples during the training, so we can fine tune some layers of the models with these new examples to follow these new formats that we want to enforce. And yeah, basically that's it. And just one additional topic that she mentioned in this topic, in this chapter, that I think it's very useful. It is the probabilistic nature of AI. So when we are working with AI applications, the one thing that we have in mind is that we have non-determinism because we are working with probabilistic models. So this is an important thing that we need to cover in all the aspects of the building, the evaluation, the deployment, the monitoring. AI applications are probabilistic by nature, and one consequence of this is that they can hallucinate, and we need to tackle it somehow. And there's some formulation on why they are hallucinate. And the first is self-delusion. So if you can it can differentiate the between the data is given with the data is generated. So we cannot like make this map to understand that this is an hallucination. The second hypothesis is like a mismatch between the labeler and the model internal knowledge. So there's no connection with this part, with these two parts. And if this response use a knowledge that the labeler have but the model don't have, we effectively teaching the model to hallucinate. So basically we are having this gap between these two, and the model don't know how to handle, and it start using his internal knowledge that is not aligned to the user preference, is not aligned with the instruction that we provide. So we start having more out of control decisions. So there are some ways to tackle these hallucinations. Like, for example, reinforcement learning could help to differentiate between prompts and tokens generated. Uh, Include factual and counterfactual signals in the training, or also in the examples in the prompt could also help on that. But also there's many other things, like for example, for fine tuning and guardrails in the post trainer, that could help also in this sense. Yeah, I think that's it for this chapter. In the next chapter, we'll talk about the evaluation methodology. And yeah, I see you there. I hope that you enjoyed this talk. Yeah, thanks. That's it.